Then let's check out the second question. Let n be a Poisson process with parameter lambda, and we define a new stochastic process as x of t, and it equals 1 if n is odd in the interval 0 to t, and x of t equals minus 1 if n is even in the interval in 0 to t. And we have to find the probability of x of t equals 1. We can easily know that the probability of xt equals 1 equals the probability of n is odd in the interval 0 to t. So we can easily find the answer, and it equals the summation of e to the minus lambda t times lambda t to the power k over k factorial. And k is odd. That means k equals 1, 3, 5, 7, and so on. So we simply let it equals an. And similarly, we can let the probability of x of t equals minus 1 equals bn. That is the probability of n is even in the interval. So bn equals the summation when k is even. We can easily see that an plus bn equals 1. It's obvious, right? So to calculate the consequence of an, we should calculate bn minus an, and we can simply write it into one formula, and equals e to the minus lambda t times lambda t of power 0 over 1, and it minus an, it minus e to the minus lambda t times lambda t of power 1 over 1 factorial, and so on. So then we can change it, so factor in the minus signal into every term. That is, it equals the e to the minus lambda t times minus lambda t of 0 power. So this minus signal does not change the consequence of this term, right? Then it plus e to the minus lambda t, and we factor in the minus signal. It equals minus lambda t to the power 1 over 1 factorial, and the same plus since this minus signal does not change the consequence of this term, so we can just add it in the bracket. It does not change the answer. And then we can easily find it equals the e to the minus t times the summation of minus lambda t to the power k over k factorial, and k is from 0 to infinity. And we have known from the property of Poisson distribution that this term equals the expected value of e to the power into the minus lambda t. So it times another e to the minus lambda t. It equals the e to the minus 2 times lambda times t. No, it equals the e to the minus 2 lambda t, right? So since we have known the answer of an plus bn and bn minus bn, we can easily find an equals the first formula minus the second formula and divided by 2. It's 1/2 times 1 minus e to the minus 2 lambda t, and bn equals 1/2 times 1 plus e to the minus 2 times lambda t. So the probability of x of t equals 1 is 1/2 times 1 minus e to the minus 2 lambda t. And the second question, we have to find the expected value of x of t. From the definition of expected value, we can know that x of t equals either 1 or minus 1. So it equals 1 times the probability of x of t equals 1, and plus minus 1 times the probability of x of t equals minus 1. That is a_n and b_n. So the expected value of x of t equals a_n minus b_n. And we have known the answer. That is minus e to the minus 2 lambda t. And then we have to find the autocorrelation of t1 and t2. That also equals to the expected value of x of t1 times x of t2. We can easily note that the product of x of t1 times x of t2 either equals 1 or equals to minus 1. So the same to the second question, it equals 1 times the probability of the product equals 1, that is this one plus this one, and plus minus 1 times the total probability of the product equals minus 1. It has two terms like this. So we can put this into, and the answer is like this formula. And by simplifying this formula, we get the final answer at equals e to the minus 2 lambda times t1 plus t2. So it's the autocorrelation of t1 and t2. And last, we have proved that if x of t is a Whitson stationary process, I think we can easily say that it's not, since the autocorrelation of t1 and t2 is not a function of tau, where tau equals t1 minus t2, but it's a function of t1 plus t2. So we can say that x of t is not a Whitson stationary process. Thank you.